Right, so last class, this was the previous question we did. We kind of stopped off abruptly here, so I'm just going to re-explain it. So Justin, according to part 3A, when you leave a charge on for 2 minutes, what was the charge that built up?
0.3 coulombs.
Right, and zero point 0.3 coulombs is the amount. So think of it like this. When we charge something, we pass in electrons. And hence we know that our electron has charge.
Yeah.
Okay, so the question is, how much electrons it will take to build up a charge of zero point 0.3 coulombs? Well, if one electron is minus 1.6 by 10 to the power minus 19, and zero point 0.3 is the total charge you get after 2 minutes, then you would just divide it. Think of it like this. If you have $10 and I ask you how much $2 it will take to make $10, you go just divide it. 10 into 2 is 5, right? Where 10 is the total and 2 is the amount of $2 you have, right? So it will take five $2 to make 10. Similarly, in 2 minutes, you leave as a charge and it reach zero point 0.3 coulombs. We're trying to figure out how much electrons it will take to make that charge. And we know that one electron is minus 1.6 by 10 to the power minus 19. That's basically it. And they get your answer. So it would take approximately 1.875 by 10 to the power 18 electrons to build up a charge of zero point 0.3 coulombs. Right? So I trust that everybody understands that. I would like you all to answer 4A and B. Try that one for me. Right, so Justin, tell me the key differences between alternating current and direct current.
Um, well, alternating current has a change in current flow.
Can't say it like that. You might get like 1 mark or something, but yeah, so you have to say this specifically. You say, um, in alternating, so you say the current
Changes direction. Wait a minute.
changes direction periodically. Right, so for AC current, the current changes direction periodically. You have to say the word periodically, right? That's the correct thing you have to use. Okay? And direct current. For direct current, you say that the direction of current is constant,
Yeah.
right? Okay, cool. Let's do part B now. So for each of the following current time graphs, state the type of current shown. Guys, what kind of current is this?
Direct.
That's, huh?
Direct.
That's direct. Because the current does not change with respect to time. It's the same exact current. If the time is 1 second, if the time is 2 seconds, it don't matter, right? So this is direct, right? Aliyah, let me see if you know what this one is. What's this?
Alternating. Well,
Yeah, you wouldn't say that as alternating. Um, Alternating means a change in direction. This not change in direction. Let me
uh,
explain what I mean by that. When we talk about a change in direction, we're talking about a change in sign. That's what we're talking about, right?
okay.
So, um, let me just say we have, okay, check the circuit here. How would the current for that flow?
From positive to negative.
Right, in this direction. If you want, we could call this positive 9 volts. Now, if I were to swap the battery, or we could say it's negative 9 volts, and we could see that the direction of the current could change. Understand?
Yeah.
Now, so what this means is that, okay, so if the current is a vector, right? Current is a vector. If current is negative, that means it changed direction. Are you seeing the current dipping below the negative axis?
No.
No. So that's technically direct current, but what that is rectified current. So if you look at the output at a rectifier, this is what it would look like without capacitors. And we would have done this if I go in circuits. I'll look check all the notes if all you want, but I know we did this. Watch. So this was half wave
Oh,
rectification, and this was
okay.
full wave rectification. So what this is rectified current. That's what it is. This is rectified current. So I will explain something again. This is not alternating current. Alternating current would mean the current is changing direction. And anytime there's a change in direction, it means there's a change in sign. The current is not dipping below in the negative region, meaning that the current is always positive, right? So Aliyah, you fully understand that, right?
Yeah.
Okay, what about the last one?
That's alternating current.
That's alternating current because the current goes from being positive to being negative.
The
There's a
negative.
change
Yeah.
in direction.
Okay.
Okay, try to remember waves. I'm gonna come back. I want you all to try 5A and B. Give that a go for me. Did you all get time to copy this down? Guys, let me know if I get a chance to copy that down quickly.
No, I was writing it.
All right, I'm coming back. Give me a second.
Okay.
Okay, cool. Does everybody have it copied down?
Yeah.
Okay, cool. Aliyah, Kirsten, I guess that you all have it copied down. Yeah, Justin, eat food. Kirsten, are you able to talk today? Taking that as a no. Aliyah, what about you? You finished with everything?
Yeah.
Okay, good. Let's move on. So the diagram below shows an electric current. State the period and peak of the current. All right. So these questions are very easy. I want to let you try it. So try the first one and the second one. I'm giving you all 5 minutes. Right. So the diagram below shows an electric current. So the sine wave goes up to 2.5 and it goes down to minus 2.5. Right? So the peak is 2.5. And the period, what is period? Period is the time it takes for one full oscillation. A full oscillation is when the graph goes up and it goes down and it returns back to the resting position, which is at the horizontal axis. Another way you can think about it is a period is a successive crest and trough. Okay? So that could be a period, that could be a period. But for me, the easiest way is looking at a complete cycle. So a complete cycle is the graph going up, reaching its peak, then it's going down, meeting its negative peak, and coming back to the resting position. So Aliyah, how much periods we have in this cycle?
2.
We have 2, right? So the periodic time t, so periodic time period is t, it is 20, and we have milli, so milli means 10 to the power minus 3 seconds. All right, so that's the period and the peak, right? So peak is equal to 2.5. You need to put the units, 2.5 amps. Yeah. So if I want to copy down the graph really fast, uh, yeah. So Justin, I didn't hear from you. Kirsten, I didn't hear from you since class start. All right. So let me know what's going on, guys. Do you all have this copy down?
Yeah, copying it.
Okay, cool. All right. Good. Let's move on. So you want to calculate the frequency. Aliyah, what's the formula for frequency again?
1/t.
Right. So frequency is a capital F or a common F?
What was that?
Frequency is a capital F or a common F?
Common F.
Yeah, frequency is a common F and the formula is 1/t, right? And whenever you use a formula, the units need to be in SI units. So we already converted the 20 milliseconds into seconds, so that's 20 by 10 to the power minus 3. So what would that be equal to? Yeah, what is 1/20 by 10 to the power minus 3?
50.
That's 50.
Yeah, good.
All right. Plain 50. Let me check that.
Yeah.
I'm in disbelief. I'm gonna check that. Okay, you're right. You're right. 50. And that means 50, 51. Was the units? What is the units for frequency? Justin, you should know this. Use a car audio, man. You know about music.
What?
What? No, no. What's his
Wait.
power?
Oh
What's
no,
his
volts.
power?
Volts.
No, what? Wait.
Huh?
No, frequency is hertz, Hz.
Oh, shucks.
Yeah, wait. If I post this on YouTube, the girls on YouTube will think like,
Oh,
wait. If your father looking at this video, he will be disappointed, man. Wait. Frequencies in hertz. Aliyah, do you remember what frequency means from waves?
I think so.
Then tell me if you remember.
Frequency is the number
the number of
waves,
oscillations
well, oscillations,
in,
um, in 1 second.
yep. So how much waves you gonna have in 1 second, according to this?
50.
Yeah, that's correct. Cool, let's move on. Explain what is meant by the potential difference for a conductor, right? I want you all to answer A, B, and C. Give me another 5 minutes. Right. So, Kirsten, I liked your definition the most for 1E. And you said that potential difference so guys, potential difference is just a fancy name for voltage, right? So potential difference, also known as voltage, refers to the difference in electrical potential energy so yeah, if I get the questions correct, please move on to the next questions. Right? So we could speed up. We still have to do logic gates and radioactive physics, right? So potential difference, also known as voltage, refers to the difference in electrical potential energy um, per unit charge in the middle of 2 points so guys, all potential energy is to get a mark, to get at least 1 mark, you need to mention that it's the difference in electrical potential energy. So you know how, depending on the height somebody's standing at, okay, let me just say we have a stick man jumping off this building versus a stick man jumping off from this building. This stick man would have more potential energy because of the difference in height. Similarly, if you have a voltage of 0 to 9 volts versus a voltage of 5 volts to 0 volts, this one would have more electrical potential energy. It's the same concept, but instead of gravitational potential energy, we're talking about electrical potential energy. And all the potential difference is just the difference in electrical potential energy per unit charge in the middle of 2 points. That's all. Right? Right. State the SI unit of potential difference. The answer is volts measured in V. The current flowing through a heating element is 8 amps. So Aliyah, tell me, what's the formula you would use if they give you current, voltage,
Um,
and you need to find power?
P is equal to IV.
Right. Right. So the current here is 8 amps. The voltage is 220. So 8 by 220 is 1,760, is it?
Yeah.
All right. A 220 main supply provides 650 watts of power to an electric device. Calculate the current supplied by the mains to the electrical device. Okay, so in this question, what did they give us, Aliyah? Tell me fast.
The voltage
They gave us the
and
voltage,
the power.
they gave us the power, right? And what we had to find.
The current.
Okay, so what formula you know have voltage, power, and current in it?
P is equal to IV.
Okay, P is equal to IV. What are we trying to find for in this formula?
I.
If I want to find phi, how would I do that?
divide by V both sides. On
I
both
would have to
sides.
divide by V on both sides. So if I
Yeah.
divide by V on both sides, this is what's going to happen. The V and the V will cancel off on the right-hand side, and you're going to end up with P over V is equal to I, which is the same thing as I is equal to P over V, right? So the answer is I is equal to P over V. Do we know what the power is?
Yeah.
What's the power?
650,
And the voltage is?
220.
Right. So what's the current?
Hold on. That's 2.95, 2.03.
Right, 2.95 watts. What's the unit for current?
Current.
Mm-hmm.
That's amp.
That's amps. Nice. All right. Calculate the energy supplied to the electrical device in 5 minutes. Okay. So let's carefully study what's going on. They want us to find energy, right? And they are giving us time. And I want you to pay attention to what we have previous or prior to this question. Look at part D. So we have the energy. So they want us to calculate the energy. They are giving us time. And what else do we have from the question? Think. So what formula do you know have energy? What formula has energy and time in it? Energy and time. Could anybody think of anything? Justin, what about you? What formula do you know have energy and time in it? As well as something from the question. What did the question mention as well?
Power.
They gave us power. So what formula do you know has power, energy, and time in it?
Well, I use E equals to PT.
E is equal to PT. All right, that's correct. Right? Alternatively, you could have said power is equal to energy over time. Right? They want us to figure out the energy, so you make energy the subject of the formula by multiplying both sides by T. Right? So you're going to end up with E is equal to PT. Some of you all will remember the formula like this and just make E the subject. Some of you all remember the formula, the direct formula, E is equal to PT. Aliyah, did you ever see that formula before? Power is equal to energy over time.
Yeah.
Right. And do we have let me ask that question. Do we have the power?
Yeah.
Right? What's the power? Given at the start of question B.
650.
650. So E is equal to 650. And what's the time?
5.
But there's a catch. Are we just going to put 5 here?
No.
And we need to convert that to SI units. So 5 minutes into SI units is what? SI unit for time. 5 minutes is what in SI units?
That's 60 seconds in a minute. So 5
Mhm.
by 60.
5 by 60, right? So that's what you're going to put into the calculator. So 650 by 300.
Um, 195,000.
Right, so your answer is 195,000 what? Eggs?
No.
Nah. What's the unit for energy? We talked about this. I remember the when we was doing energy and we talk about demand, all kind of thing, and we talk about caloric theory and like the Cannonball experiments, and we talk about the man who come up with energy.
That's what June?
Yeah, joules, right? So cool. Next one. This one is very hard. I wouldn't lie. I'll give all you some time to work on it, right? Take some time, work on that. Okay, we still have a good bit of questions to do. Let's move on fast. If we want to finish in time, I feel like I gotta do this question with Talia. Based on the
I
amount
think
of
I get
questions
the
we gotta
answer.
do.
I think I
Huh?
get the answer for it.
Well, let me see.
I
So an
think I don't know
electric,
if it's correct.
oh, we go see, right? So an electric motor is connected to a 6-volt supply. It draws a current of 0.4 amps and lifts a 0.6 kilogram mass through a distance of 1.5 meters in 20 seconds. Gravitational field strength, G, is equal to 10 newtons per kilogram. What does gravitational field strength mean? That's a fancy way of saying what? Somebody tell me. Gravitational field strength is a fancy way of saying what?
Force?
Hmm?
Force?
No, the units for force is newtons. Like the units for this is newtons per kg. Aliyah, what is gravitational field strength? It's a fancy way of saying. Guys, I had to know this. G. G is what? Anytime I see G in physics, what's G?
Force.
No. Again, the unit for force is newtons. The units here is newton per kg. Anytime I see G, G is what?
Ground.
Gravity. Gravity.
Gravity.
G is gravity. G is not grams. G is gravity. So gravitational field strength is just another way of saying gravity. So the information they're giving us is they're giving us, let me just write down all the information, shall we? So they're giving us the voltage, V is equal to 6 volts. They're telling us the current, I is equal to 0.4 amps. And they're giving us mass, it lifts a mass of 0.6 kg. And through a distance of, so they gave us distance, maybe that might be valuable, I don't know. Distance of 1.5 meters. In 20 seconds, they gave us time. And they gave us gravity. Gravity is 10. Gravity is 10 Newton kg, newtons per kg. So that's all the information we have. And keep that in mind. That's all the information we have. So with that being said, Ali, I would like you to calculate the power supplied to the motor. What is the power supplied to the motor? Alia, what is the? I would like you to figure out the power supplied to the motor. How will we do that? Is there any formulas we know for power? Look at the
Yeah.
variables we have. And tell me if you have any formulas you could use there.
Mm-hmm.
What formula we could use?
P is equal to IV.
Right, do we have I and V?
Yeah.
Okay, what is I?
I is 0.4
What is V?
and V is 6.
Right, so what is 6? What is 6 by 0.4?
2.4.
What is the units for power?
What?
Watts, that's correct. Justin, this is way how to say watts, right? Calculate the work done in raising the mass. Okay, all right. We need to figure out the work done. Hmm. Is there any formula for work done, you know? When we talk about work done, work done is another way for saying what? What is work the definition of? Like, okay, if I say that, I'll give away the answer. Can't say that. What is work done? To do work, what you need? Alia, to do work, what you need?
Energy.
Right, so work done means energy. So is there any formula that you know deals with energy? And look at wait the information I have. Look at all the information I have. So we need to figure out the energy, right? We need to figure out energy in raising the mass. See if you can figure out that. Right? Justin, let me check what you have here. Aliyah, if you figure out anything, you'll let me know. Did I ever? I believe I did send you all this, but I'm sure I'll lose it by now. I probably lost in the chat long time. I'll have access to all the formulas in physics. There was a document that had all the formulas in physics. Do you all have it?
I think so, yeah.
Or do you want me to send it back?
Yeah.
Okay, I'll do that. Maybe that might help
And
you.
the formula is E is equal to PT.
Waiter. Let me get this real quick. All the formulas here. All right. Give me a second while I send the formulas. So earlier you were telling me E is equal to PT. Earlier.
Yeah.
Okay. I'm gonna send all the formulas and you tell me if you still agree. Keep in mind there are multiple ways we could do the question. Um, I'm gonna send it. Yeah, so it have all the formulas there. Check it. All right, so here what? I sent you all the formulas, or the formulae, so check it through. All right, so I'm gonna answer part B. So Aliyah, you there, right?
Yeah.
Okay, so they want us to figure out the energy in raising the mass. Now you said E is equal to PT, right?
Mm-hmm.
I want you to hold on to that. In the question, you are raising the mass some distance up. Because you are raising something up, what kind of energy is that? So you're raising something up. What
Right.
kind of energy are you using to lift it up? Let me explain. anytime we have height, anytime height is a factor, what kind of energy are we talking about?
Um,
There are two types of energies you need to know for this, for CSEC physics. Can you tell me the two types of energy? Well, at least see ones with formulas. Check the formula sheet. Should have the formulas for energy.
yeah. E is equal to I VT.
Hmm.
Is that one right?
So I want you to check under energetics. Check under energetics, right?
Okay.
There are multiple formulas. There's work is equal to force by distance. There's power, P is equal to E over T. But
Mm-hmm.
you can use that formula to find for energy. There's kinetic energy and there's gravitational potential energy.
Yeah.
Which formula there directly involves height? Which formula there has height in it?
Um,
And look at what they give you. Look at the variable. Look at the values they give you. They give you
mhm.
they give you gravity, right? They give you mass. They give you
So
distance,
gravitational potential energy.
right? Think about it like this. By the object being on the ground, it has potential energy in the sense that if you have to lift it up, you would need to go against gravity. So by the fact that it's on the ground, it has potential energy, has the potential to be lifted up. I guess you
Yeah.
could think of it like that. If an object is moving, it has kinetic energy. If it's if it's on top of a if it's on top of something, so think of it like this, right? If you have an object on top there, earlier, and it has the potential to fall down, and because of its height, and if it falls, it will accelerate downwards.
Yeah.
Okay, so anytime you have a stationary object, it has potential energy. Now, what's going on here is that you have an object and we want to lift it 1.5 meters. We have an object with mass and we want to move it up. So anytime that's the case, we're talking about gravitational potential energy. So the formula for gravitational potential energy, that would be mgh, right? Do you understand why this was the most suitable formula to use? Because it had mass, gravity, and height.
Yeah.
All right. So what's the mass?
The mass is 0.6.
0.6 here. What's the gravity?
Gravity is 10.
What's the height?
The height is
So in other words, the height is the distance in which you're make it whether fall down from or you're lifting it up to.
that is 1.5.
Yeah, 1.5. So plug that into the calculator and let me know what you get. So you get like 9 or something.
You get 9.
Justin, I'm very impressed. Like actually, I'm very impressed. Give my box. Well, give my box. Well, Justin figured it out by using a different method. It's the same working, it's just he separated to parts. Excellent job. Right? So 9 joules. Okay, cool. That's the answer. Aaliyah, you said you wanted to use E is equal to PT?
I ever say that? No.
Yeah, you did say that at the start, remember? E is
Yeah.
equal to PT. Now let me explain what's the problem with this. If you find that, you're not gonna find okay, so if you do this, you're gonna figure out how much energy the motor use. You're not gonna figure out the raw energy it takes to raise the mass. Let me explain something. Aaliyah, do you think the motor will be 100% efficient in lifting the mass? When I say 100% efficient, do you think all the energy we are supplying to the motor will be used perfectly, without waste, to lift the mass?
Um,
Let me ask you a question. When you drink Lucozade or something and you intend to do work and you get energy, do you use all that energy to do work or do you procrastinate?
Please use the energy.
Yeah, but she's also use the energy to procrastinate.
Yeah.
Yeah, so is the procrastination useful?
No.
No, so you're wasting energy there. It's the same
Yeah.
concept. When you supply power to the motor, not all of that, not all of that energy is going to be used to lift the mass. Some of it is just going to be released as heat and because of friction. So when you find E is equal to PT, you calculated how much power you're supplying to the motor, not necessarily the
The energy.
the energy you would need to
Oh, okay.
lift the mass.
Yeah.
Yeah. So, but let me see what we would get. So we know that power is equal to energy over time, and like you said, energy is equal to power by time. What's the power? Alia, what was the power?
The power was,
Alia.
yeah, the power was 2.4.
What was the time?
The time was 20.
How it's a multiply that from
I think the answer was 48.
Okay, that's a lot more energy than I want you to notice that, eh? I want you to realize that. I want you to see it. See it. You see it?
Mm-hmm.
Again, listen to what I'm saying. Do you think the motor, just like you, just like us, I procrastinate a lot as well. You have the energy, but is all the energy being utilized to do something meaningful?
No.
No. You ever feel a fan and your fan was hot?
Yeah.
You know why? Okay, and heat is another form of energy. Justin, I'd like you to pay attention. Even if you got the question correct, you still have some things here you could learn. Unless you want me to talk to your mom. No, your dad. Your dad.
No, I don't hear that questions.
Okay. Well, I want you to just pay attention for this, like briefly, right? Briefly. Um, Justin, no machine is 100% efficient. And let me explain what I mean. Justin, when you're playing music, your car arms will be cool or it's get hot.
Let's get hot.
Okay, heat. Is heat a form of energy?
Yeah?
Yeah, heat is a form of energy. But do you want to arm to produce heat energy?
No.
No, you want it to amplify the sound. So, and some of the energy being wasted as heat.
Yeah.
Right, so it's not 100% efficient. Aliyah, your fan does get hot. It's not 100% efficient. Some of the energy being lost. And if some of the energy is being lost, and you would need to put in more energy to actually get something done.
Yeah.
Okay, so Aliyah, how much energy do you actually need to raise your mass?
9.
9. But how much you had to put in to do the same thing?
9.
No, 48. That is how much work the motors, that's how much energy the motor has to output to do to lift the mass. Because the
Oh.
motor is not 100% efficient. Some of the energy is going to be lost to heat. So what I'm trying to say is, what we calculated here was the theoretical actual amount of energy it would take. What we calculated here is how much energy you would have to supply to the motor in order for it to raise the mass effectively, because it's not 100% efficient. Do you understand that? Sure.
Yeah.
So explain it to me then. What's the difference between this one and this one? Wait. Calculate. I do that, right?
Um. Okay. So the energy you're putting in to get the work done all of it doesn't go into that.
right? Not all the energy is going towards lifting the mass.
Yeah.
Okay.
Mhm.
So if you put 9 joules of energy, and you waste some, would you be able to lift up the mass?
No.
No, so you have to put a little more to
Yeah.
account for the procrastination and the absolute waste of time.
Yeah.
I wish I could have seen your face when I look at you, right?
Uh,
So what we do in here is we calculating the theoretical amount. This is how much energy in a perfect world it would take to lift the mass. But this is how much this is how much energy you actually putting into the system to lift the mass. Okay? So again, guys, write down the information you have and you can see we can make patterns. So they gave you the mass and the distance and the time. Well, we don't really need the time there. They gave us the mass, distance, and gravity for a reason. Okay? Calculate the power output of the motor. Aliyah, um I think this is where it would talk. So how would I figure out the power output of the motor? How would I figure out the power the motor was given? Come on.
easy.
So the power
Um,
output of the motor.
that would be P's. P is equal to
Now you have to be careful here, right? In the previous one, we calculated the power supplied to the motor, but we understand, Aliyah, we understand that the power are supplied to the motor, not all the power is going to be used to actually lift the mass, right?
yeah.
You understand that?
Yeah.
Okay. So if we supply in 2.4 watts, we need to figure out how much power we actually need to lift the mass. Okay, that's what we're going to do. So we're not going to use P is equal to IV. We're not interested we don't care about that. Let's utilize what we have. In these questions, typically you had to use what you find previously to answer the question. So they made us find for energy or work done. So we have work done. Is there any formula for power involving work done and time?
Yeah. P is equal to E over T.
Right. So the energy we need to lift the mass is 9 joules, and the time it takes to lift the mass is how much?
20.
20 seconds. So how much power do we actually need to lift the mass?
You need 0.45.
Right, I need 0.45 watts. So Aliyah, are we 100% efficient? Are we using the exact amount of power to lift the mass? Or do we have to put more power?
You would have to put more.
Right, because again, it's the same concept. When you put power into a system, not all the power gets used for what you want it to be used for. So,
Yeah.
Aliyah, how much power do I actually need to lift the motor? I mean, not lift the motor, lift the mass. What's the actual amount of power I need to lift the mass? Aliyah, you can do this. Everything is here. Remind me, how much energy did I need to lift the mass?
9. No.
Okay, I needed 9.
Yeah.
And using that, we figured out the power.
Right.
So we lifted, so we needed to supply 9 joules of energy over a time period of how much seconds?
20.
20. So in other words, how much power do we feel like in an ideal world? How much power do we have to use to lift the mass?
0.45.
Right. But how much power are we supplying to the motor?
2.4.
Right. So let me ask you a question. if I was to ask you how much of the power is being wasted, what would you tell me? How much power is being wasted?
1.95.
1.95? Yeah, 1.95 because we actually need 0.45. Why are we supplying 2.4 watts?
Yeah,
Mhm.
yeah.
So that brings me on to the last thing, calculate the efficiency of the motor. If you want to figure out the efficiency, it's the power output all over the power input multiplied by 100. We're comparing how much power we need for the output versus how much power we need to supply. So Aliyah, what was the power input and what was the power output?
The power output was 0.45,
Right? And that was over a power input of
2.4.
2.4, right? Multiplied by 100. What how efficient was the motor? Multiply that for me. 0.45 over 2.4. Do you think the motor was efficient?
No.
No, it all think about it. You needed to supply 2.4 watts to get the motor to lift the mass that really needed 0.45 watts to be lifted.
Mm-hmm.
So the motor, a lot of the energy that's applied to the motor was lost as heat and because of friction. Remember, a motor is something that spin, right?
Yeah.
You remember? Yeah, a motor is something that spin, so it's susceptible to losses via heat caused by friction. Anything that moves has to face friction, right? If you rub your two hands together, you see, if say your hand will get hot. Again, that's because of friction. So even though we put in 2.4 watts, we don't really need that 2.4 watts. We actually need 0.45 watts. But
Yeah.
because because we didn't utilize how much we put in, a lot of it was wasted, right? And that's why we see it inefficient. So did you get 18.75%?
Mm-hmm. Yeah.
Okay. I was yapping a lot, but I have to make sure I understand the concept because this is a lot of maths. This right here, you're looking at 1, 2, 3, 4. You're looking at 12 maths. It's a lot of maths. We don't want to get something like this wrong. Very easy maths. Alia, what if they said that the mass was moving? How would you calculate the energy of it then? Any object
See.
that is moving possesses energy by virtue of, it says motion. So what kind of energy would you need, what would it have? If an energy is moving, it possesses what kind of energy?
Kinetic.
Right, kinetic energy. And you would need, to be low kinetic, you use a half mv squared, right? Justin, I would like you to explain how you did the question. I know how you did the question, but I want you to explain to Aliyah and Kirsten how you did the question. You broke it up into parts.
Yeah.
So, answer part B.
Part B?
Oh, yeah, part B. Part B was the one I believe you did slightly different. Yeah.
Yeah.
So explain to them how you did
Um,
it.
well, I think force is equal to the mass multiplied by the gravitational field strength. They give it the
Because,
mass as um
right, so if you use force is
0.6
equal to
kg.
mass times acceleration, because
Yeah,
gravity is acceleration, right? They say that the force was equal to 0.6 by 10.
by 10. Yeah. I
So the
get
force
6
was,
Newton.
right, and what do you do next?
After that, for work done, I take force multiplied by the displacement.
Right, so energy is equal to force by distance, right? So that will be 6
6 by
by 1 point,
1.5.
right? And I'm
I
getting the
got
same answer.
9 joules.
So that was perfect. So that was another method, Gills, right? Yeah. Justin and I roll today, boy. I don't feel like you use AI for that because AI wouldn't give you the answer. So I feel like I could trust you. Trust that the answer is something that you do. Yeah,
Nah, I didn't get that from AI. I do that by myself.
yeah, I could tell because I mean, any question I give all you.
Even if you use AI, I don't think it will give you a so detailed answer.
Now you go do it like how I do it. Because how I do this is the most straightforward method. How you did it was a more human approach. That was awesome. Good job. So I'll go send these questions on the chat. Don't bother to copy down too much now. Right now we're just focusing on being able to do the questions. Right. So let's continue with question 3. Aliyah, I'd like you to read question 3.
A filament lamp is connected to a power supply. A current of 0.1 amps
Mm-hmm. Yeah. Current of 0.1 amps.
flows through it for a period of 20 seconds. The
Right.
energy, okay,
Yeah. Continue.
the energy dissipated
Dissipated.
in
Dissipated.
the lamp is 240 joules.
Right. Part E.
Calculate the charge passing through the lamp in 20 seconds.
Right. So Aliyah, first things first, I want you to pull out the information. What did they give you?
They give you the current,
What was the current?
which is 0.1
0.1 what? 0.1 Aliyahs.
I say amps.
Oh, amps. Okay, okay, yeah, yeah. Then yeah. So you said Aliyah Ramakan.
No.
I don't want to give you.
Time,
They gave it time. Time
which
is what?
is 20 seconds. And they give you energy, which is 240 joules.
Right. So they want you to figure out charge passing through the lamp in 20 seconds. What formula you know? So they want you to find charge. What formula you know? Let's calculate charge given these parameters. Not all three, eh? Could be like 2 out of the 3.
Okay.
What formula you know? Yes, Aliyah, what formula you know? We used the formula last class. Charge.
I wasn't here last class.
Oh yeah. You sure? I swear you was here last class.
No, I wasn't here.
Okay. Well, look through the notes. I mean, look through the formula, the formulae. I
Okay.
say proper thing.
Um,
What formula will you use to find charge? Charge.
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 Q is equals to IT.
Right. So charge is Q, and to calculate charge, you need I and T. Do we have I and T?
Yeah.
Awesome. This is the strategy I want all to use all the time in maths, physics, chemistry, anything. Pull out, write the information you have. So I 0.1 and time 20. Yeah, what's 0.1 by 20?
That is
0.1
two.
by 20. How much?
Two.
2?
Yeah.
2 what?
Cool.
2 coulombs, yeah. Right. So everybody okay with that? Justin, you get that? Okay, nice.
Yeah.
Justin, you did get that. Right? Calculate the potential difference across the lamp. Now, potential difference, we know that is just voltage, right? We know that is just voltage. All right. So Aliyah, they want me to find voltage. This one might be a little harder, but look through the formulas. See if it have any formulas where you have voltage, charge, and things like that. Check through. Check through the formulas.
Um, voltage.
So you're looking for a formula, right? Let me explain. Again, here what? Most likely, you'll have to utilize what you just now found in the previous question. This is a recurrent trend. What you find in the previous question?
Q. So V is equal to E over Q.
V is equal to E over Q. Yeah. That's the trend, right? That's the trend. Typically, where you find previously, you'd have to use it in the next question. The formula you have to use is E. E is equal to
V is equal to E over Q.
apologies, man. V is equal to E over Q, right?
Yeah.
Okay, cool. Do we have E and Q?
Yep.
Yeah, because it gave us the energy. Energy is 240, and we found the charge,
Which is 2.
right?
So 120.
Let me ask you that question, right? Um, the filament lamp is the bulb that they used to use long time. It's it is connected directly to the ceiling. Right, Justin? Until you just stick that into the wall. Well, not to the wall. I'm talking about this light.
Yeah.
And until you just put it directly into the ceiling. Or you know how much or you know is the voltage in your house?
No.
Justin. Attempted to tell you go ask your father now. Attempted.
Axel?
Go ask him fast. Go ask him fast. Ask him where's the voltage go ask him where's the voltage in the house. While Justin doing that, Aliyah, um, you guess where's the voltage in the house? The main voltage. Where's the voltage in the house?
Um,
If you don't know where it is, here what to do. Pick up your phone charger and look at the voltage rating. Uh, I'm sure you have a charger.
yeah.
Okay,
They say
right?
the input is 100 to 240 voltage.
Okay, 100 to
Volt.
240 volts, right? So
Yeah.
from that, and you just plug that into the wall.
Yeah.
So your voltage in your house is between 100 to that range, right? The typical
Okay.
voltage in your house is what, Justin?
He's sleeping.
Eh?
He's sleeping. I got to ask him.
115 to 120. So this makes sense. When you put a bulb into the ceiling, it is be supplied with 115 to 120 volts on average, right? Sometimes 110. That will range. This makes sense. So Ali, are you okay with everything so far?
Yeah.
So what's the strategy you think we're using now? What's the strategy? Ali, what's the strategy? Let me hear.
Um, hmm.
So what's the first thing we just do? in this question and the last question, what we doing? What's the first thing we doing?
We write down all the things that they give you.
Exactly. And you figure out what you're trying to find.
Yeah.
You look at the variables and you try to figure out what formula have all those in it. Next thing, whatever you calculate in the previous question, be prepared to use it in the next question. So if you're looking for a formula, keep in mind what you just now find. So you find for Q, you have to find for V. What formula have Q and V in it? V is equal to EQ. Again, they gave you energy at the start, so you already had to combine everything.
Okay.
Right. Okay, draw a label diagram of a dry cell. I'm not gonna waste anybody's time. This might take a little while, so I'm gonna get a diagram on Google and put it on the screen. By the way, guys, what's a dry cell? Do you know what's a dry cell? I don't think I teach all of that, but
No, you didn't do that.
try to figure out what it is. What do you think a dry cell is? I'll give you a hint. It is produced direct current. What's a lino? Does produce direct current. Come on, guys. What was the simplest was the easiest example of something that is produced direct current?
Battery.
Yeah, a dry cell is just a battery. That's what a dry cell is. Right? So looking for a good diagram. Does everybody know what batteries look like? Guys, okay, you know what batteries look like, right?
Yeah.
Cool. I have a question, right? And it will all make sense. Justin, what's the most popular battery?
Duracell.
Okay, I want you to listen back where you just now say. Say it word by word. Dura.
Cell.
Hmm. And I ask you guys, where's a dry cell? Think about it. That's where they get a name from. Dura cell. Dry cell.
So a Duracell battery is a Duracell.
Yep. All the batteries is dry cells. Once it's not rechargeable, it's a dry cell. Yeah. Yeah, so that's the basic concept. I'm trying to get that. All right, so let me share my screen. Ali, I hear what I tell Justin. What is the most popular battery?
Duracell.
A Duracell. And funny enough, this is obviously not by chance. A dry cell. Duracell. Any battery that can't be recharged is what we call a dry cell. Wet cell batteries are like batteries you have in your phone. They can be recharged. But I think that's beyond the scope of what I don't know. It's not listed in the syllabus, at least. So a dry cell, a simple battery that cannot be charged. So again, I'll send this after class. Draw a labeled circuit diagram to show how a car battery can be recharged. Okay. So guys, based on what Justin, you know about car batteries?
Really.
Oh.
Yeah.
Okay, you think a car battery is a dry cell battery or a wet cell battery?
That's so.
A wet cell. And you just see like a little liquid in the battery. And you just hear them talking about that, like if it have acids fill in the battery or something, soap something. So you know
Yeah.
what I'm talking about? Well, yeah, a car battery is an example of a wet cell battery. And if dry cell batteries cannot be charged, do you think a wet cell battery can be recharged?
Yeah.
Yeah, right? So a car battery is an example of a wet cell battery. Wet cell, and that means it could be charged. And let me get a diagram real quick. So basically, to charge a battery, you just need a battery charger, which is output DC current, and hooking up that to a battery. So I'm gonna give you a simple, very simple diagram. Right? Very, very simple. Guys, Justin, uh, I would like you to answer a question, right? Justin, at home, was he main voltage we use at home?
Uh, well, this is like 120 to 150
And that's DC voltage or AC voltage?
AC.
Yeah, that's AC voltage, right?
Yeah.
What's something good about AC voltage? What you could do? We could do with AC voltage.
Could change the direction of the current flow.
No, AC voltage is already changed. What's so cool about AC voltage? What we could change in it? We do that. We do that recently. AC voltage, we could do what with it? We could change its using a. We could change its blank using a. So Justin, a car battery. How much volts is a car battery?
Um, Good question.
What? No. I have to talk to your dad. Nah, boy. Justin, you had to tell your dad to teach you these things. A car battery is 12 volts. Typically, it's 12 volts. So think about it. If you're charging your car battery at home, will you just stick that into the wall? First of all, a car battery is DC. The current in the wall is AC. That's our problem. Second thing, the voltage in the wall is like what 120. The car battery is 12. What we need to do with the voltage first,
Lower down.
right?
Well,
We will lower it down using what? What we
I
did
just stop.
lower down?
Doing stop.
No,
Transformer.
a transformer. Remind me, a transformer. What does a transformer do again?
Transformer uses concept of a constantly changing magnetic field to induce the voltage.
Okay. Um, So that explains why we need to use AC. Remember, if we don't use AC, it wouldn't have a change in magnetic field. Remember, in alternating current, the direction of the current is switch, and if that's switching, then the direction of the magnetic field switching. So yeah, that has induced the EMF and current in the secondary coil, right? Depending on the number of turns, the voltage could either raise or it could decrease. Remember?
Yeah.
So I'm gonna do a simple circuit diagram here, right? I guess this is a little extra. So you have your mains voltage over here, right? So this is 120 volts AC, right? You have your transformer here. There's your okay, Justin, remind me, if you want to step down voltage, you want more turns in the primary or the secondary?
Do you want to step down the voltage?
Yeah, you want to lower the voltage. You want more turns. Remember, more turns equal.
More
What
voltage.
does more turns mean? Lower voltage or higher voltage?
Higher.
Higher voltage. So if you want to lower down the voltage, you want more turns in the secondary or less turns in the secondary?
Less.
You want less because less means lower voltage. So we're gonna draw plenty turns in the primary, right? And we're gonna do less turns in the secondary. Alia, you ever look at the notes? Were you there for the transformers?
Intro to Transformers.
Yeah, when I was doing transformers, you was there?
Yeah, yeah.
Okay, cool. So what I have here, I have a step down transformer. So the step down transformer,
No, no, wait, I don't think I was here for this class. I just write down the notes.
hmm, well,
Yeah.
a transformer is something that is convert, but it don't convert. It is just either raise the voltage or decrease the voltage, right? And how it is work is you have an alternating magnetic field. If you have an well, guess you can say that. A transformer does work only with AC current. The reason why, were you there when I did Faraday's law?
Yeah.
Okay, so Faraday's law says that anytime you have a change in magnetic field, you have an induced EMF. So, in the primary coil, I have an alternating current. If you have an alternating current, is the magnetic field changing or remaining the same?
Changing.
Changing, remember, anytime you have current passing through a wire, you can use your right-hand grip rule to figure out the current. But well, so in DC, the current is going in one direction, but in AC, it is switch. And if it's switching constantly, the direction of the magnetic field changing, and so you have a change in magnetic field. So what others do, right? So you have a change in magnetic field here. 1 minute it's going like that, next minute it's going like that. It is induce a voltage and a current in the secondary coil. And depending on the number of turns, that go either raise the voltage or decrease the voltage. Less turns means less voltage. So what we need to do is we need to have a circuit here that lowering down the 120 volts to the 12 volts, right? And we need to put it in a bridge rectifier. What is the purpose of the bridge rectifier? Do you recall? Alia, tell me if you remember, what is the purpose of the bridge rectifier?
No.
No, things looking kind of grim, you know. A
Wait,
bridge rectifier just converts what?
oh,
A battery does work with AC current or DC current.
D.
DC current.
Yeah.
So AC current wouldn't work, so we had to use a full bridge rectifier to convert the alternating current to direct current. That's what we have
yeah.
this here.
Yeah.
And we did this in class. I remember doing it in class.
Yeah, that was when you was.
It's just now that we combining everything kind of hard. Like you gotta remember everything, and it's like kind of a little hard.
Yeah.
But, yeah, I feel like this might be a little too complicated, but it's not that hard to understand. And we did everything here. It's not like we didn't do anything. I'll re-explain it when I'm finished with the diagram. So Leah, let me just explain what's going on in the diagram, right? Um, so over here, this is the car battery. This over here, this is the rectifier. This over here is the step-down transformer. So we have everything, right? So Leah, let me just run through what's going on here, right? So we have we hook it up. So we want to charge the battery, the car battery. So we're gonna so like you see how your phone charger does work? It's the same kind of concept here. So what we're gonna do is we're gonna plug it into the wall. But Aliyah, if we want to charge a car battery is 12 volts, right? Mains voltage is 120 volts plus its AC. That's two issues. Is 120 volts too high or too low?
That's too high.
Way too high. That's crazy. So we need to
Yeah.
lower it down to 12 volts because a car battery is 12 volts, no? So you would use the appropriate step-down transformer, and the step-down transformer would change the 120 volts AC to about 12 volts AC. But it's still alternating current. Is a battery alternating current? Does a battery
No.
use alternating current?
No.
Well, I say that kind of bad. A battery doesn't use current. It gives current. And a battery produces direct current, not alternating current. So,
Yeah.
Aliyah, when you use a battery, what happens is it loses the charge, right? It loses electrons. So when you're charging it, you're pumping back electrons into it, right? That's what you're doing.
Mm-hmm.
So the first step, you need to convert the 120 volts AC to like a more reasonable 12 volts AC, but it's still alternating current. So what's the next step? What's the next step we had to do with the alternating current?
You have to change it to DC.
Right, and that's why we use this. We have a full bridge rectifier. It has 4 diodes. Unfortunately, you need to remember this. You need to remember this, right? You need to remember the orientation of the diodes. So you just have to remember this. So you have two diodes pointing in the opposite direction. So like these diodes over here pointing in the same direction, and these diodes here pointing in the same direction, right? In the middle of them, you're connecting it to the alternating supply. The other two connections is the direct current. So the rectifier is converting the alternating current to the direct current. So Aliyah, it converting this to this. That's what we're doing. Right? So once it converts the alternating current to direct current, you can now hook it up to the battery and now pump back electrons into the battery and charge it. Yeah, that might be a little hard for you to understand. I had to explain it back next class. Yeah. So we still have questions to do. We still have some questions to do. It would help if all you do these questions for homework. So the next class we can speed through it. I want to do one more question before we leave. One more question. So let's do one more question because I did start class late. So Aliyah, I want you to read D4, question 2, quickly.
Christmas tree lights are connected in a series
Oh
and
wait,
a parallel.
we'll do these questions next class. Right? We'll do these questions next class. Yeah, Tama?
Okay. Christmas tree lights are connected. Wait, hold on.
Yeah.
Sorry about that. Christmas tree lights are connected in a series and parallel arrangement. 4 lights are connected in series and are called string A. Another 4 lights are connected in a series and are called string B. String A and string B are connected in parallel. A. Sketch a circuit diagram showing both string of lights.
Okay, let's go. So you have Christmas tree lights are connected in a series and a parallel arrangement. Remind me, what does series mean? You remember series and parallel configurations? Justin and Aliyah, do you all remember parallel and series configurations? I'm not hearing from any of you guys. I want to to identify which one is series and which one is parallel. Which one is series? 1 or 2?
1.
1. 2 is parallel. Anytime easiest way to figure it out is in a series circuit, the current typically goes in one direction, one after the other, and in a parallel circuit, the current splits. Right? Aliyah, remember?
Yeah.
All right. So 4 lights are connected in series. Okay, so 4 lights are connected in series. So we're gonna have 4 bulbs, right? Tell me if you understand that. That's A. So I have 4 lights in series. Um, and then they're saying another 4 lights are connected in series. Wait. 4 lights are connected in series and are called string A. Another 4 lights are connected in series and are called string B. String A and B are connected in parallel. Okay, so this is string A, and we have string B, which is the same thing. Very bad diagram. Right, so we have string A and string B connected in parallel. That's it. Right? Yeah, Ali, are you confused by that? So they're saying I have
No.
string A. String A is just 4 lights in series,
Mm-hmm.
and string B is 4 lights in series, and we connect it in parallel.
Yeah.
Am I confused by that?
No.
No? If string A alone is connected to a power supply, explain what would happen if one bulb were to blow. So if we have a series connection, right? Imagine you have a bunch of bulbs, and we connect this to a battery, right? So all of them working, so the current passing through, right? But if one of the bulb blow, what happen? In a series circuit, if one of the bulb blows, what would happen? Ali, I want to hear from you. Let me just say that the bulb in the middle were to blow.
Um, all the bulbs could be.
Well, all the
Like
bulbs
it
wouldn't
wouldn't light.
blow.
It wouldn't light.
No, it wouldn't light because if it's blow, that means the connection on the inside break. So will the
Yeah.
current be able to fully pass
No.
through? No.
No.
So if one bulb were to blow, the rest it would create an open circuit. That's the answer. So an open circuit would be created. An open circuit would be created, and all the bulbs would cease to light or something. Basically the other bulbs wouldn't light, wouldn't turn on, right? An open circuit would be created, and the other bulbs will fail to light. As power supply is connected across the parallel arrangement of string A and string B, explain what would happen if one bulb is blown in string B. So Aliyah, actually I'm gonna call Justin. Justin, so we have this situation, right? And we're saying that it connected to a battery. Positive. So Justin, if one bulb blow in string B, what will happen?
The others would not light.
Well, let me see. So the current will come like this. Current split in here. Over here, the current goes split like this, but since this bulb low, it wouldn't be able to reach this bulb. So what gonna happen to this whole line up here? So Justin, let me explain that again. If a bulb blow, so like we have a parallel configuration. What that means is the current is passing through this and it's passing through this. But if a bulb here blows or anywhere, that would create a open circuit, meaning that the current wouldn't be able to pass through. Justin, you there?
Yeah.
So if the current can't pass through, like for this stretch, so like if this bulb low, will the current be able to reach these other two bulbs?
No.
So will the current be able to reach back the ground, the negative?
No.
No. But if we look at the top, will the top, what about the top? Is the current flowing?
Yeah.
Yeah. So if if one bulb in string B blows, then all the bulbs in string B will stop lighting. But all the bulbs will continue working. All right, so an additional. So wait, Justin, if we no longer supplying power to string B, then hence all the power will go to string A.
Yeah.
You think string A would start to light a little brighter?
Yeah. Because more current going
More
to.
power. Right. Because they're not being divided again. Right? Additionally, the bulbs will shine brightly, will, will shine brighter in string A because the current isn't being divided. Yeah, right? So I will send the notes. But that's pretty much it. Next class we have this to do, we have this to do, this to do, this, this. Oh, quite a lot. Yeah. So how much pages, boy? Let me see. We have 1, 2, 3, 4, 5, 6. There are like 6 pages to do. We're gonna see if we can do the next class. Right? So yeah. Aliyah, you okay?
Yeah,
Aliyah, what principle does a transformer
force.
depend on to work? A transformer works on a principle of what?
AC current.
No, but you have
No.
a point. A transformer wouldn't work with DC current. How to use AC
Right.
current? You're not wrong, but it uses the concept of mutual what?
Induction.
Yeah, that's it. Right? So cool. See you guys next class. Hopefully we will finish up this. Yeah.
Okay,
And we
bye.
have some magnetic questions to do as well. Yeah, this is a very long topic. Oh, wait a minute. Wait a minute. We still
Hold
have
up, something
magnetics
to
to
do?
do. Yeah.
Okay.
Okay, wait. But you know what they say? Never back down, never what? Never give up. That's what they say. So we're not gonna give up. Yeah, we're not gonna give up. Right, Talia?
Okay. Yeah, for sure.
Yeah. So later, guys. Please try to be on time next class so we could do as much work as possible because it's quite a lot. Yeah. So later,
Okay.
everybody. Thanks for coming to
Bye.
class. Have a good night.